Let's go ahead and get started. Thanks everybody for attending this webinar. This is Kyverno Deep Dive. This is part two of a what, why, and how webinar series where we look at Kyverno, the Kubernetes native policy engine, and tell you more about it, how it works, some of the use cases it can solve. And in this case, I'll be going into more depth on what it can do and also demonstrating each of these capabilities from where we left off in the first part. So thanks everybody for being here. My name is Chip Zoller. I am a Kyverno maintainer. I am also a technical product manager at Nirmata, the company behind Kyverno, and have been working with the tool for a few years now. Let's dive into the agenda. So first, since this is a deep dive, not going to rehash a bunch of the things that my colleague Anusha, who is on the webinar with us today and will be able to field questions that you might have while I'm going through things. So she left off with a good overview of Kyverno. So I'm just going to do a super quick high-level overview once again of Kyverno in one slide, just for those that may not have attended the first section. And then we're going to pick up with the remainder of those capabilities. So Anusha showed validation and how that works from a general perspective. Now I'll show the remainder of the capabilities and also demonstrate how each of those things works. So we'll talk about mutation, the ability to change resources. We'll talk about generation, the ability to create new resources, image verification, how you can verify image signatures and attestations, and also some of the new features in 1.9, which we just released, new cleanup policies, which allow you to actually remove resources, and policy exceptions, a separate resource that allows you to provide decoupled and general exceptions to other policies that might be installed. So for a super quick overview, Kyverno is an admission controller that's purpose-built for Kubernetes. It is not a general purpose admission controller. Because it's purpose-built for Kubernetes, one of the things that we wanted to do was have you be able to write policies simply and easily by recycling the skills, knowledge, and tools that you already had, which means that policies are written all as standard YAML. There's no portion of it that's YAML and then another portion that's a programming language. And so, as the next point mentions, there's no programming language required, either knowledge of one or use of one to express policy decisions. Kyverno hides all of the difficulty and exposes a simple interface, just how you would do other things in Kubernetes native ways. Like, for example, we're used to accessing or requesting pods using just standard YAML. We can do things like asking for certificates in YAML. We can even build whole new clusters and infrastructure that's in public cloud providers by defining YAML. We think you should be able to do the same thing with policy without having to use an esoteric language. Kyverno is also the most popular, at least by stars, policy engine that's out there. And part of that is due to the fact that Kyverno has a lot of interesting capabilities, some of which aren't found anyplace else. So validation is the ability for you to deliver a yes or no response and according to a policy and a resource. So here's a policy that says these things must be there or these things must not be there. And here's a resource. Do you allow it, yes or no? That's validation. That's where most policy engines begin and end. That's only the tip of the iceberg when it comes to Kyverno. Now, I'm not going to cover validate here because Anusha did a good job of covering that in the previous webinar. So access that recording if you'd like a primer on validation. Mutation is an ability to change a resource. So a user submits a resource or a process does, and you have a policy that says, I want the resource to be modified in some way. Mutation is that modification. You can have Kyverno modify resources, including existing resources, by the way, and part of that I'll show here, based upon a policy definition that you define. Generation. This is one of Kyverno's seminal and most favorite capabilities that I find, which is its ability for it to create new resources based upon a definition and a trigger that you define. And so I'll show more about this as well. And verify images. Kyverno can, in addition to doing things like the validation checks, which are yes or no, should this image be allowed or not based upon the registry from which it originates, it can also crack that image open, or rather look inside of the OCI registry for artifacts that are attached to that image and see if things like signatures and attestations are present. And if they are, Kyverno can allow that image into the cluster based upon signatures and attestations. And also cleanup, which is a new capability in 1.9. Cleanup allows you to delete resources based upon a policy definition. All of these things can be done without use of any programming language, using standard YAML, recycling the skills and knowledge that you already have. The capabilities here that are highlighted are ones that I'll be showing in this webinar and also demonstrating. So mutation. Mutations modify resources. They mutate the existing resource, or they mutate a resource that comes in. This occurs during the mutating admission phase. So there are two phases that occur in Kubernetes. One of them is the mutation phase. That's the changing phase, the one that we're talking about here. And the latter one, the later one, is the validation admission phase. So Kyverno is going to be mutating resources that come into the API server during this phase, which is the first phase. Mutations are, this is a nice trivia point, are serial. That is, they occur in serial order based on the number of mutating webhooks that you have defined, and they occur in lexical order by name. So mutating webhooks that start with A run first, then the ones with B, so on and so forth. One thing to be aware of is service meshes. Service meshes are typically doing things like either injecting containers into pods or adding labels or annotations or some other thing. So you want to be aware of what you have in a cluster that's also performing mutations. Mutations that are subject to Kyverno will have already been mutated by the API server. So be aware of this as well. When you're doing things like testing for these, you want to know what the API server is going to already be doing to resources before you ask Kyverno or anything else to additionally modify them. In Kyverno, these mutations can be specified in one of two different ways. One of them is a standard JSON patch. This is RFC 6902 compliant, and you specify that with the patches JSON 6902 definition, and also a strategic merge patch, which, if you're familiar with Kustomize, this is the same patch strategy that Kustomize uses, where you define a portion of the resources that you want to have added, not the full representation of the resource, only a subsection of it. And that's defined with the patch strategic merge directive. Mutation in Kyverno, in addition to it working for new resources that come in, it has a capability which allows you to mutate existing resources that are in the cluster that don't have operations done against them. So this can be super helpful when it comes to things like, for example, adding labels to an existing namespace. So Kyverno can do both of these things with a single policy definition. Do be mindful if you're using GitOps controllers. Typically, GitOps controllers will expect that they are the owner, either of an exclusive owner of the resource or a significant portion thereof. And there are different ways to handle this depending on which GitOps controller that you use, but do be cognizant of, if you're using GitOps, then you will need to make some slight modifications on which resources and how they get accommodated for, but that it does work perfectly fine with it. And so with that, let's flip over to a demo. And so each of these things, I want to show a demo because this is a deep dive and we wouldn't be diving deep enough if it weren't for that. So what I'm going to show in this first demo is how Kyverno can mutate existing resources to actually solve a real valid use case. So here's the problem that happens in the Kubernetes space. Very often, things like secrets and config maps are consumed as environment variables. And so therefore, in pods, when you run the application that's inside of the container, they have access to a number of environment variables that are defined on the pod. The challenge is, if you go later and update the secret or config map, which is consumed as an environment variable, the pod and the container has no way to know and get that updated value. This is something we can actually solve in Kyverno. Rather than having you go and manually do a rollout restart or some other thing like that, Kyverno can be the engine behind this process, which watches it and then makes changes that effectively restart pods. So what we're going to do here is have a deployment, and the deployment's going to reference an environment variable here called token. And this token is going to come from a secret called blue secret. And what we want is the deployment that's already running out there. If we update the secret, then we can get the new value automatically. And we're going to use Kyverno to do that. So the first thing that I'm going to do is to grant Kyverno some additional privileges here. And the reason that we need to do this is because the way that this is going to work is rather than us having to manually do a rollout restart, we're going to have Kyverno mutate the deployment to add a label, or maybe it's an annotation, I can't remember. Kyverno is going to do that. So it needs permissions to update these existing resources. And this was an example of being able to update or mutate existing resources in addition to new resources. But in this case, we're going to update an existing resource. So I've just applied the cluster role, which is going to grant me those additional privileges. Now I'm going to create my secret. Now, in this case, I've just got a secret that is simulating an API token. This could be anything. It doesn't matter, but you can see the value that's up here. This ends in 628. So let's go ahead and apply this secret. Now we've got that secret that exists. And now let's create the deployment, which is going to reference this. So blue secret, and we're going to pick up the key called token. And we got the deployment. So let's take a look at the existing namespace and get pods. And let's exec into this one that's running with our secret and just get the environment variable. So there's the token, and you can see from what I showed just a moment ago, this is the value that we expect. Now what I want to do, this deployment's up and running happily. We want to tell Kyverno to take action on this if that secret changes. So I'm going to introduce a cluster policy, and a cluster policy is going to function across the cluster. And so let's just break this down briefly, not going to boil the whole thing, but we want to watch for changes to any secret that's labeled with kyverno.io/watch equals true. This could be whatever that you want, but I'm narrowing this down because I want to watch only secrets that are labeled with this to know what to do with them. I'm only going to care about updates to those secrets, not if somebody creates a new one. And if those conditions are true, we are going to mutate existing deployments in whatever the namespace in which that secret was updated, because you have to consume a secret in pods that are co-located. And what we're going to do is add an annotation called corp.org/random. And this is the value that you see here is one of Kyverno's super cool capabilities. It has a number of filters that allow you to provide custom behavior based on a definition. And so in this case, we're going to write a random string that Kyverno is going to generate for us. That's 8 characters long, which we define here. And this could be anything, but this will make sure that we have some unique value that gets written to that, so that if we update the secret later, we get a different value, thereby causing new pods to get spawned. And we're going to just make sure that it's only going to do this if the name corresponds to the name of the secret that was triggered earlier. So a few things going on here. This is definitely more advanced than your standard mutation, but this is also a deep dive, so showing you how to get some more mileage out of these capabilities than just standard mutation. So I'm going to apply this cluster policy. And now that this cluster policy is created, what I want to do is go and change that secret. So the secret that we're watching, I'm now going to change the API token, simulating some process in your environment that might be doing this for an API token or some other thing. So we're going to change the value to 5 echo 2. So just keep the last bit in mind. And here's the encoded value in base 64. So let's apply this. And what I expect to have happen, I'm going to try and do this quickly, is to flip over. We should see new pods spawned. And when those new pods spawn, they should be picking up the new environment variable. So let's do that. And now let's flip back over. All right, so I'm putting out a watch on this, and you can see quickly, this one was running. Now we're creating a new one. This one comes into a running state, and now we're terminating this one. So this represents the new pod. So let's exec into this one and see if we actually got the new secret value that we expect. And you can see here, in fact, we did. The new pod that was spawned as a result of Kyverno mutating the deployment resulted in picking up the new value of that secret. All of this happened in an automated fashion without me needing to do anything else other than creating that cluster policy at that time. So you can see in this case, this is a real world use case that helps you where you are today to be able to provide some automation for cases that you may not have. Or in other cases, you might be using like bash scripts, you may not have an answer for it, or you may be using one-off tools. Kyverno can help to kind of close the gap and reduce some of that burden. And all of this by defining policy as code. And none of this involves a programming language. So with this, you know what you're going to get, and it's predictable, and you know how you're going to get it. So that's it for the first one here. Let me just clean up, and we'll switch over to the second one. All right, so let's flip back over. So that was the mutation one, and I hope you can see an example of how powerful this can be, but that's really just the beginning. We've got a lot more to go through. So generation. This is the ability for Kyverno to create new resources, and this can be any resource based on a trigger that you define. So imagine a namespace gets created, or a deployment gets created, or whatever else gets created, or updated or deleted. It's up to you. And in response to that, Kyverno can stamp out some new resource based upon what you define. And this works for custom resources as well. So you can have custom resources be functioning as the trigger, as well as be the thing that Kyverno generates. It makes no difference. If it's a Kubernetes resource, Kyverno can generate it. New resource definitions that will result in the generation, you can define them in the policy itself, and this is called a data type. This is where inside of the policy definition, you declare what the resource looks like. So the spec field and whatever else, you put all of that data in the policy inline, or you can clone it from an existing resource that's out in the cluster. You can say where that resource is and what type it is, and that you want to simply pick that up and copy it down in number of times. The nice thing about this is, in addition to that initial generation, it has a synchronization feature. And that's one of the things that I'll show here. Because if something happens to whatever the source is, whether that source is defined in the policy or whether that source is a source that you define elsewhere in your cluster, subsequent changes to that, if you elect, can also be propagated down to wherever Kyverno generated that. So super useful in making sure that resources are in sync across a number of namespaces in your cluster. Now, some of the common use cases for generation, why would I want to do this? Think of things like multi-tenancy or namespace as a service. Whenever I generate or create a namespace, I need a network policy, a resource quota, a limit range, role binding. You need these things typically in these use cases. Well, you don't necessarily have to define those, 50 times for 50 namespaces. You can just define one policy, and then you go about creating your namespaces, and Kyverno will handle everything else. And this also works on existing items as well. So things like existing namespaces. It's not necessarily realistic to say, all right, I only want generation to occur on new namespaces or whatever the new construct is that comes after the fact that this is introduced. You're also probably going to have some sort of a brownfield environment. I've got an existing cluster with a whole bunch of existing namespaces, and it sure would be nice to get some of this benefit just by introducing a policy. Kyverno can also do that without you having to do anything separate. So let's show this in action. Let me flip over and show generation in action here. So in this use case, here's the challenge that we're trying to solve. Typically in enterprise environments, you have things like a custom certificate authority that might represent PKI from your enterprise root CA. It could be anything, of course. It could be a configuration option of a lot of different things, but very commonly, we do see that certificates are used. You need this certificate, this config map, to be consumed in a lot of different namespaces, because if this is, for example, a CA certificate, you probably have pods or other workloads that may need that certificate in order to trust those resources that exist across the cluster. But similar to the previous problem that we talked about, if it's a pod, it can only reference other namespace resources in that namespace. So now you have this problem of, I need to be able to consume this config map in multiple namespaces. So now you have to have the config map in multiple namespaces. Well, it would be super nice if Kyverno could manage that for us. So all we have to worry about is managing a central config map in one namespace, and everything else Kyverno manages for us. And so that's what we're going to do. Let's say that we have a namespace that we want to consider for that central resource hub, and it's going to be called our platform namespace. And in that, we want to create a config map that we're going to call org.ca, and this is your organization certificate authority. Again, it could be anything. And I'm just defining a standard certificate. In this case, this comes from my internal lab environment where I do have an enterprise root certificate authority that runs, and I have to be able to trust it against other resources that run in my Kubernetes environment. So I'm going to create this. And now I'm going to introduce a Kyverno policy, which is going to do a couple things. One, it's going to give me that that config map in existing namespaces because I'm introducing this in a brownfield environment. And also, if I create new namespaces, it's going to do that. And it's going to clone it from my platform namespace. So you can see here, we're going to match on any namespace. Doesn't matter what it is, we're going to respond to any namespace. And we're going to generate a config map with the org.ca name. And we're going to synchronize that. So we're going to watch the source config map in case that changes, and we're going to respond. And we're going to clone that config map to any of the namespaces that were caught by this policy. So let's flip over and first create this config map. So we'll create our config map org.ca. And now we will create this policy. And let's take a look at some of the namespaces that we have. So in my existing namespace, it's cleverly named. Let's see if we have, and we don't have this config map. So I expect a couple things. First, when I introduce this policy, because I've said I want it to apply to existing resources, I expect that as soon as I introduce this policy, that it's going to clone that config map for me right now. And the second thing I expect is if I create a new namespace, it's going to do the same thing and clone that config map in a new namespace. So let's see if this actually happens. So I've just created the cluster policy. And now let's go back to the existing namespace. And we can see, as of 3 seconds ago, I just got the org.ca config map in that namespace that it was cloned from our platform namespace. And now that's great, but you're going to create new namespaces after this as well. And so we want that same behavior to occur. So let's create a new namespace. Let's be super creative and call it new. Very original here. And what we expect to have happen is Kyverno saw this event and it also cloned that config map there. And you can see indeed it did. And if we inspect the contents of either of these, any of these config maps, you'll see that they are identical to the org.ca config map that's in our platform namespace. And so, although I'm not going to show it, if I were to go now and make a change to this CA certificate that's in my config map, Kyverno would observe that event and go and propagate those changes downstream. So you can see with the generatability that this now is becoming a much more interesting thing than just a basic policy engine that can do yes/no responses. This can really be a powerful tool. And all of these capabilities can be combined in a lot of different ways so that you can get some really advanced and cool automation to help you with your jobs working with Kubernetes day to day. So that's it for this one. Let's flip back over. First, let's get set up for the next one. So let's flip back over to slides and keep on trucking here. So image verification. This is a rule type that Kyverno has that allows you to check container images for things like signatures and attestations. And what this is useful for is ensuring your supply chain security. It's great to be able to ensure that you're only pulling images from allowed registries, but you need to go a step further in ensuring that the images that you do pull, even though they may come from a blessed location, that they've actually been created and signed and certified by your organization. And right now, Kyverno has a capability of doing this using SigStore cosign. We are bringing support for Notary v2 very soon. But regardless of what the provider is, Kyverno is going to do two potential things. One, it has the ability to look at the signatures that are attached to your image and verify that those signatures are what they should be according to a policy definition. And if you're using attestations, these are things like provenance, software bill of materials, vulnerability scans, or it could be anything custom. Whatever you attach to it, you also have to go through a similar process. You have to assert who's attesting to it and use a key method or maybe a key list method as cosign allows. You want to make sure that those attestations are correct, that they're present, that they're correct, and that they are in place before you allow that image to get pulled into the cluster. Kyverno can do all of these things. And what I'll show in this demo upcoming is how you can do this to get started with image signature verification, which is really the first and best place to get started with this. Kyverno supports attestations in the in toto standard format. In toto is a CNCF project. And this is indicated by a rule type called verify images, which you'll see shortly here. The nice thing about this is, though, it's integrated directly into Kyverno. It's not a bolt-on approach. It's not something that you need to install separately from a separate provider and plumb the two up. If you don't want this capability, or if you do want it, you simply request it by adding a policy that specifies that you want to verify signatures and attestations. There's nothing else for you to do. There's no knobs that you need to turn on. There's nothing else that you need to deal with. It's all there out of the box. This runs during the mutation and the validation admission phases because we need to be able to do things like associating a tag, which is mutable, with a cryptographic digest, which is immutable. So we want to, as part of the process of ensuring that the signature is good, we want to make sure that the signature is good specifically for that one image and not just any other tag. So that's a high-level overview of image verification. Now let's get into this by actually showing it in action. So let's flip back over here. And what we want in this case is we have a number of pods that are container images that we're building internally. As almost all organizations that run Kubernetes, they're not running off-the-shelf software. They're also running homegrown software that they build and they package as container images, and then they consume in their Kubernetes cluster. What we want to be able to do is have supply chain security and assurances for those applications to make sure that all the way throughout the build process and through running, that the image is what we expect, it's correct, and we've stamped off on it with a key. And so what we're doing here in Kyverno is ensuring that any images, and I'm just using a test image here from the Kyverno repo on GitHub Container Registry called test verify image, but you can imagine this could be either star, meaning every image that comes in, or a number of different images. We want to make sure that this is signed by a public key that we're specifying here. So you can sign with your private key and keep your private key separate. That's a little bit more of a difficult problem when it comes to verification, or rather securing that private key. Cosign does have an ability called keyless signing, and Kyverno can verify signatures that have been signed with either of these mechanisms. In this case, I'm just going to use the keyed method because this is something that we see pretty commonly in enterprises. So that's what we're doing. We want to make sure that this image, any tag from this image, has been signed with this public key. So let's go over and first see that we want to see that this is in action, but we want to see if this is going to catch something that's unsigned first. So in this image, I'm going to run the unsigned tag. This is just a bare pod. What I expect to have happen is, because I have a Kyverno policy that's saying, you told me to check any test verify image to make sure that it was signed with that key, I'm going to check every tag for that image. Well, this tag corresponds to an image that has not been signed, so we expect that this is going to be denied. And let's see what Kyverno does. And as you can see here, let me just increase the window. Kyverno said, nope, no matching signature for that. So it's not that the image repository itself did not have any tags that weren't signed, it's that this specific one was not signed, and so we're not going to allow this into the cluster. Now, I can also change the behavior to audit, which may allow you to accept such images, but to see them in the result of a policy report, which can be an effective way for you to provide non-blocking behavior, but still know these are the images that I wanted to have signed but weren't. But in this case, I do have an enforce mode, which is going to deny that from running. So conversely, what we want to have happen, if we point it to a signed image, we want that to be run, because in this case, the signed tag is signed, and it's not only just signed, but it's signed by a private key that corresponds to the public key that we defined in our policy should match for that image. So let's try this once again and see if Kyverno permits it. And you can see here that Kyverno checked the image, it checked the signature on it, it compared that against the public key that you specified in the policy and allowed that to run because there was a match. So you can see here with image verification, this is a good way to get started with supply chain security just by starting with image signature verification. With Kyverno, this is a super simple process. There's no additional component that you have to introduce to your cluster. There's no additional knobs that you need to turn. You can just simply introduce a cluster policy like this. And by the way, all of the ones that I'm showing in addition to others, are available on the website and in the Kyverno policy repos. So you can really just copy and paste most of these things and get this behavior that I'm showing today, or use these as inspirations on how to develop and customize policies for your own needs. So let's clean up this and get into the next one. And let's flip back over here. All right, so cleanup policies. This is a new capability that we introduced in Kyverno 1.9. This is an ability for Kyverno to remove resources. So you saw with the generate capability, we were able to create resources, and that's super helpful. But it would also be nice, either complementary to or just in separation of generation, to be able to additionally clean up resources. Because when you have a Kubernetes cluster, you have a bunch of users typically and other processes that are using it. There are all sorts of resources that are landing in it. Some of those might be from GitOps controllers. Some of those might be manual user created things. Leaving resources around not only consumes resources, as in memory and CPU, but in case of cloud environments, it incurs additional costs. These cleanup policies are introduced with a new custom resource called a cleanup policy. So previously in Kyverno, we had a cluster policy and we had a policy, the latter being for cluster scoped actions and the former being for namespace scope. We have a similar thing with cleanup policies, a cluster cleanup policy and a cleanup policy, cluster cleanup policy being for cluster scope resources and cleanup policy being namespace. This will delete matching resources on a schedule. The schedule portion is important because you want this to typically happen on a recurring basis, not just a one and done thing. As I mentioned, it has cluster scoped and namespace scoped variants, so you can choose whichever one works for you. And this uses a tripartite expression, so a three-part expression that you're already familiar with in Kubernetes for finer selection of the resources that you want to select. So things like key, operator, and value. You're familiar with these in Kubernetes because they're used in a lot of different locations. Kyverno also uses that same construct, which allows you to be very fine-grained as far as which resources you want to select. Since this is a new feature, we are trying to phase this out in two different approaches. This is the first phase that we've introduced. The second phase is we would want to allow things like self-labeling. So a user can just simply assign a label either at the time a resource was created or after the fact in an update operation, and have those automatically be cleaned up either on an absolute time or after a certain timer has expired. So that's kind of what we're thinking of bringing down the line. This is implemented in a separate deployment. So when you install Kyverno, you get a separate deployment, which is the cleanup controller. So be cognizant of that. And also be cognizant of the fact that you will need to add permissions because Kyverno ships with only the minimum permissions that are needed to operate. If you do want the cleanup behavior, and Kyverno will tell you about it if you've not done it, you will need to add permissions so that you can tell Kyverno it's okay to delete the resources that you expect. So with all that said, let's flip over and look at a demo of the cleanup controller. So here's a common problem that the cleanup controller may solve. You have what may be referred to as bare pods or naked pods that are running out in your environment. Typically, you don't create bare pods. They're owned by a high level controller like a deployment, a daemon set, stateful set, maybe another custom resource that triggers pods. But sometimes you still do need to do spot checking. Maybe it's troubleshooting, like in a break glass scenario, you have an outage, somebody needs to get in there and check connectivity. Maybe you need to curl an application. There are a lot of different cases where you may need to imperatively run something that you normally wouldn't do. But like what so happens so frequently, we run those things and they do the job, and then we put our tools down and we walk away, job done. So we've forgotten about them. But like I mentioned, these things are out there potentially running, potentially incurring costs. You really want to be able to clean those things up, but you want to do so carefully and on a select basis. And you may need to do this on a scheduled basis, not just a one-time, well, let's go and remove all the troubleshooting pods or something else that we created. But in this use case, let's imagine that these are troubleshooting pods that got spawned. So as I mentioned, bare pods are pods that are not owned by a higher level controller. So we should be able to find these and be able to remove these. Now, here's an example of a new cluster cleanup policy, which is going to operate across the entire cluster. And it's going to do this. And it's the way it's going to do it is it's going to match on all the pods that are out there. And here's an example of the expressions that I was talking about. Here's an expression that says, go and look at the owner references of all of these pods. Now, without getting into too much of the detail, owner references is a portion of a pod where it declares what the owner of that thing is. And this is where you would see something like a replica set, for example. And in turn, a replica set may reference a deployment. But if it doesn't have any of these, we can conclude pretty safely that this is a bare pod. And now we want to remove those bare pods. And then we just put in the schedule in cron format of how frequently we want this to run and identify those bare pods. And in this case, I'm just running it every 1 minute. This is probably not something that you want to do in production. In fact, I'd recommend that you not doing it. But for the sake of accelerating this demo, let's do that. So first thing that we need to do here is to give Kyverno these permissions. As I mentioned, we're very cognizant about being security first and following the principle of least privilege. So we need to tell Kyverno that it's okay for you to remove pods. So we're going to give it that permission right now. Now we've done that, let's create some of these bare pods. And you can see I've got 3 of them here that are going to go in a variety of namespaces. So I've got a pod that's in an ing namespace and a platform namespace and an existing namespace. So let's go ahead and create these bare pods that are out there. And I'm just going to run a standard BusyBox image, and it's going to sleep, simulating a pod that's still out there running. Maybe you use this for an exec, and so you need a shell. But anyhow, it's a pod that's just out there running, chewing up resources, really doing nothing. Now I got 3 of them, so maybe you had dozens. And now let's introduce this cluster cleanup policy that I just showed, and let's take a look at what happens once we do this. So now we just introduced that cluster cleanup policy. Let's take a look and see clean Paul is going to be the alias for this. So we just created our clean naked pods policy, and it's going to run on that same schedule, just created it a moment ago. So let's go and take a look at the pods that have this run BusyBox label. And I'm going to look at them across there, and let's just watch on this for a moment, because what we expect to have happen is when this fires, and hopefully we should see this firing any time now, those pods are going to go into a terminating state, indicating that Kyverno found them as part of the definition of the policy, and it cleaned them up. And as we can see, they're now going into terminating state because the cleanup policy snapped into action and it found those, and now it's cleaning them up. So as you can see, the cleanup capability can be super useful, again, to you as platform engineer, or just in general, if you're a cluster operator or maybe security minded, you can really use this to remove things that may just be causing clutter in your environment. And it's very complementary to a lot of the other capabilities. So you can have this clean up whatever resource that you want, including custom resources. So that's a little bit about cleanup policy. And let's clean up, no pun intended, this, and flip over to the last one and then get back into the slides. So policy exceptions, the second major new policy type that we introduced in Kyverno 1.9. This is a new custom resource called a policy exception. And a policy exception decouples the exclude block out into its own resource. So the exclude block is a component of a standard Kubernetes policy, which allows you to narrow the scope of resources to which the policy will apply. So a match throws the biggest net, if you will, and then the exclude block filters out the things as a subset of that you don't want. The challenge is, prior to policy exceptions, for you to provide that fine-grained filtering required you to go and modify that policy. Or for more advanced use cases, you could do things like update a central config map that had some of the policy definition in it. But what we heard was that was a little cumbersome for teams, especially of a larger size, and that had a lot of diversity as far as roles that were required to modify a cluster and be able to one group being responsible for creating policies, but another group being responsible for creating resources, and they don't necessarily talk, and maybe it's cumbersome to go and respond to every request and update every policy. So we decoupled the exclude block into its own resource, which allows you to exempt any policy and rule combo based on the presence of a policy exception. These policy exceptions are namespaced, so you have to create them in a namespace. There's no cluster scoped variant, but any policy exception can still exempt something no matter where it is. It's just that you must create it in a specific namespace. You can exempt from a cluster or a cluster policy regardless of what that type is. So typically, and this is what I'll show in the demo in just a few moments, we typically see this associated with things like exemptions from validate rules. But this can be used to exempt it from any type of rule that you're capable of writing with Kyverno, not just validation rules. And this can exempt from a cluster policy or a policy. We don't provide an API for how this gets really controlled as far as a lot of the checks and balances that are concerned, but you can use things like standard Kubernetes RBAC. Because this is a new custom resource, you can easily declare who should be allowed to create policy exception resources. You can use your GitOps flows that you're using today and your GitOps tools to deploy these. And even Kyverno validate rules, because Kyverno can validate any Kubernetes resource, not just your out-of-the-box resources like deployments and config maps and what have you. You can use a Kyverno validate rule to validate a policy exception. And also this includes things like manifest validation, which we didn't have time to get into here. We could do a deep dive on each of these topics, but in manifest validation, Kyverno can actually check the signature of a YAML manifest. We talked about doing that with an OCI image. It can do the same thing for a YAML manifest. You can sign these policy exceptions, perhaps in your GitOps pipeline, or maybe it could be standalone. And Kyverno can validate that before it even accepts that in the cluster. And you can use any of these methods or all of these methods to gate what happens with policy exceptions. So that's probably enough said. Let's take a look at the flow. This is just a better illustration of maybe my definition. So you have you're starting off here and you've got a validate policy that's in enforce mode. Maybe this is something like making sure that all pods, let's make it uniform across the board, all pods must run privileged mode false, so cannot run privileged. And so normally, if you sent a user or process sent a resource that violated that policy, it's going to block it unequivocally. But with policy exceptions, Kyverno is going to check and see, does there exist a matching policy exception for this rule and this policy? If one exists, yes, then it'll allow it. If not, then it'll block it. And it'll tell you about it either way. So if it allows it, then it'll let you know in a report, hey, just want to tell you this resource was allowed. We know it violates this resource, but it's because you had a policy exception over here that it was allowed to run in the cluster. So let's actually go and see this. So I'm going to go over to my exceptions, and let's first take a look at the cluster policy here. Now this is a basic one, and this is a validate rule, just to make the principle clear. So imagine that you have a cluster policy, as many people do, that define best practices in your organization. And one of the common best practices when it comes to governance are things like ensuring that resources have whatever labels that you want attached to them. In this case, we're saying that all config maps must have a label called team. Can have any value, doesn't matter, but a config map must have a label called team. Obviously, you can extrapolate and add multiple labels and say that these need to be on pods or what have you. But for this case, this will suffice as just an illustration. So config maps must have team. So normally, if we create this, if we attempt to create a config map that does not match that definition, we will get a blocked message in response from Kyverno. Hey, you had a policy that was out there, said you had to have team, this didn't have it, we're going to block that resource. But with the new policy exception, and here's an example of that policy exception, we're saying, look, it's okay. Any policy name called require labels, you can exempt the rule called require team, but only provide an exemption for a config map named emergency. Now, in a policy exception, you have access to the full array of Kyverno's match and exclude capability. So I could go even further and say additional things like it has to be created by a user named Chip. It can only be in this namespace, a lot of other things. So you can get very fine scoped. And in fact, this is often a good thing if you're going to provide an exception, because it doesn't make a whole lot of sense to have a policy that says, going back to the example that I used earlier, all pods in the cluster must not run privileged, and then a policy exception that says, nah, let all pods run as privileged. That probably doesn't make a whole lot of sense. You want to finely control how that happens. Again, you can use things like Kyverno validate policies, and we even have an example of this that's already built for your use in the library that can do exactly this. So anyhow, if we create this policy exception, what we want to have happen is the config map that we saw that was previously blocked, which is named emergency, is now allowed. So let's install this exception. And now that we have the exception, let's try this same creation. And we can see here that the config map is now allowed. And you'll notice that I didn't modify the cluster policy in any way. I just created the policy exception, and Kyverno checked to ask, is there an exception there before we do anything else? So that's really it for the policy exception feature. And that is a conclusion of what I wanted to show, and hope this has been useful as far as not only describing from a higher level what the capabilities in Kyverno are, but let's actually look at these in more depth and see how they can work and in real life scenarios that can be useful to you. All right. And if there are no other questions, let me thank everybody for attending today. And please feel free to follow up with us if there are any further questions offline. Thank you.